Welcome back to day 2 of Law of Sines. Previously, we had talked about how law of sines could be used to help us solve for the missing sides and angles of any given triangle, regardless of if it's a right triangle. Today, I want to talk a little bit more about the ambiguous case. A triangle is considered ambiguous when we are given two sides and a non-included angle of the triangle. When this happens, there's 3 possibilities that could occur. We could have a situation where there's no triangle formed. We could have a situation like we've seen before where only one triangle is formed, but we could have situations where there are 2 triangles formed. We must check if we say that there's no triangle formed. We must check to see if the 3 angles are still going to add up to that 180 degrees. Now recall the law of sines. The law of sines says if you take the sine of any angle, we'll call it angle A, over the side across from it, that will be equal to the sine of the next angle over the side across from it, which will be equal to the sine of the third angle over the side across from it. So keep in mind angles A, B, and C, and we're referring to the side across from angle A as being side A, across from angle B, and across from angle C being side C. Now, why does the ambiguous case exist? When you think back to geometry, it exists because of can the triangle be formed? So if you looked at a situation where, let's say that we needed to form a triangle along this black line. I knew that I needed there to be a 30-degree angle. So there's that one angle that I know already. I also know that I'm going to give you one side that is 6 inches long. So there's that one side that we're given. What triangle can I form if I know a second side that is 5 inches? So as we see, here's one example of a triangle that could be formed with that 5-inch side, the 6-inch side, and that 30-degree angle. But what if we drew the same triangle? Here's my same, I want to draw that same triangle along this black line. Once again, there must be a 30-degree angle. Once again, I must have this one side that is exactly 6 inches, and I must have a second side that is exactly 5 inches. I could draw that 5-inch side going toward that 30-degree angle and create this much, you could call it smaller, obtuse triangle versus this larger acute triangle. So we have these 2 different situations. In terms of the trig, think of it in terms of the size of this angle. Let's say that this second angle, we're given this 30 degrees. Let's say that this angle came out to be 25 degrees. Okay, well that 25-degree angle would be here in the first quadrant, and we know in the first quadrant that the sine of that angle is positive. But we also know that the sine of that angle is positive in the second quadrant as well. So we know that there's the second angle, that reference angle is still 25, and there would be this second possibility of an angle of 155 degrees that would also have the same sine value. So when using law of sines, we have to look at could both of these angles, this 155 degrees and this 25 degrees, could both of these angles make reasonable triangles? Okay, example 1, looking at how we apply this. So here's an example of the ambiguous case. If it is ambiguous, you must ask yourself, are there 2 triangles? So the reason you have to ask if it's ambiguous is so that you remember to check this. Now, in going on with using law of sines, just like we've done in the previous lessons, start with the one piece of information where we know both parts of the ratio. For example, we can say the sine of that 25 degrees over 1 is my first ratio. Now, the only other side that we're given here is this side 2, so we're going to write our second ratio to allow us to solve for angle A by saying the sine of angle A over 2 would be equal to the first ratio. In solving for the sine of A, I'll do the sine of 25 times 2, and the sine of 25 times 2 is approximately 0.845. To find angle A, do inverse sine of that 0.845 angle A is about 57.7 degrees. So if I come back up here, I know that angle A is 57.7 degrees. If this is 57.7 degrees, then to find angle B, all I need to do is subtract both known angles from 180. 180 minus 25 minus 57.7 is 97.3 degrees. Once I know angle B, I can use angle B to help me find the side across from it, side B. Now again, I would encourage you to go back to the original ratio that you were given, sine of 25 over 1 equals, and now we can write my new ratio, sine of 97.3 over side B. To solve for side B, I'm going to be doing the sine of 97.3 divided by the sine of 25, which means side B is about 2.35 when rounded, 2.35. I also would encourage you to double check your measurements as we've talked about before. Make sure that the largest side is across from the largest angle. Make sure that the smallest side is across from the smallest angle. It's a quick way to confirm that your work makes sense. But now back up to the original question. Since this was ambiguous, we have to check, is there a second triangle that could be formed? So if we come back to this angle A, and we're going to go back to the part that we had already started here. We started by solving and finding out that angle A could be 57.7 degrees. But on your unit circle, that 57.7 degrees is in quadrant 1, which means that there's a second possible angle over here in quadrant 2. That angle would be 180 minus that 57.7. Minus 57.7, which means that angle could be 122.3 degrees. So what if that happened? What if angle A, instead of being 57.7, what if angle A was 122.3 degrees? Now to find angle B, I would once again subtract the two known angles from 180. 180 minus 122.3 minus 25, meaning that now angle B is 32.7 degrees. Now I have all three angles. Using that last angle, I can then find side B by once again using my sine ratios. Go back to the original sine of 25 over 1, and now I can write my new ratio, sine of 32.7 over side B. To solve for side B, we will do sine of 32.7 over sine of 25, which means side B is, side B in this case is 1.28. And again, double check the measurements. This time, here's my smallest side, 1. It's across from my smallest angle. This time, 2 is my biggest side, and it's across from my biggest angle. So once again, it still makes sense. Here's an example of a situation where, even though we were given the same piece of information, we have two very distinct separate triangles. This triangle has, well, they actually are both obtuse triangles, since this one also has an obtuse angle. But we have a second very different obtuse triangle with a very different set of angles in it. Okay, second example here. Okay, another situation, is this ambiguous? Again, since we do have two sides and a non-included angle, yes it is, and therefore we have to ask, is there a second triangle? Okay, start by solving for one of the angles in the first triangle. If I write my first ratio, sine of 40 over 3, and then write a second ratio, sine of C over 2, the sine of C would be equal to the sine of 40 times 2 divided by 3. So the sine of 40 times 2 divided by 3 So the sine of C would be about 0.43, which means angle C, when I do inverse sine, angle C would be 25.4 degrees. As one possibility, if you think on your unit circle, so we're saying angle C could be 25.4 degrees, but there's also a second possible angle in quadrant 2 that would have that same sine value. That angle would be 180 minus 25.4, which makes that angle 154.6 degrees. Now pause and think about our second example. If you go back to the first problem, if angle C is 25.4, we could easily find angle B by subtracting from 180. 180 minus 40 minus 25.4 would give me this 114.6. In my second case, if angle C was 154.6 degrees, would I be able to find angle B? This time the answer is no, and that's because that 40 plus that 154.6 is already bigger than 180 degrees, which means that even though there were two possible values for angle C, this one will not work since it will not form a triangle. Now, we can still finish the problem. We do know that we have now angle C. With angle C, we've concluded that angle B had to be 114.6 degrees, and we could still find side B by setting up and using our law of sines. So here's a case where, even though it's ambiguous, there is still only one triangle that can be formed. Okay, case 3. Case 3 is another ambiguous. We have two sides and a non-included angle. So we'll start by writing the ratio, comparing the two known pieces of information, sine of 75 over 6. Then we'll write our second ratio, sine of B over 8. To solve for sine of B, we're going to do sine of 75 times 8 over 6. Sine of 75 times 8 divided by 6. That means that the sine of B is approximately 1.29. Right away, since that ratio is larger than 1, we know that this is undefined. And because this is undefined, means that there is no triangle. So we've seen examples of all three kinds. In our first example, we had two distinct and separate triangles, and in this particular case we did have to solve for all of the missing sides and angles of both unique triangles. We saw a second example where there was only one triangle that could be formed, and therefore we only need to solve for the one triangle. The second triangle, because the angles would be over 180, can't exist. And then we do have a third situation that, due to the ratio being greater than 1, this triangle can't exist originally, which means there can't possibly be a second one. One final example, though, since we've seen one of all three of these, and now this one we don't know which scenario it could be. Remember, if it's ambiguous, you must ask yourself, can there be a second triangle? The answer could be yes, the answer could be no, but you must ask yourself that question. So if we start solving this one, start with the two pieces of information. Sine of 35 over 6 allows us to find the sine of C over 8. To find angle C, we'll do sine of 35 times 8 divided by 6. Sine of 35 times 8 divided by 6. Oops. Sine of 35 times 8 divided by 6. The sine of C is approximately 0.76, which means angle C, when I do inverse sine, is about 49.9 degrees. Now keep in mind that there are two possible angles for what angle C could be. So angle C could be this 49.9 degrees, or angle C could be in the second quadrant, and it would be 180 minus 49.9, which means the other possibility for this angle is 130.1 degrees. What we need to decide is, will both of these possibilities work? So in the first situation, if angle C is 49.9 degrees, then to find angle B, I would have to do 180 minus 35 minus 49.9, which means angle B would be 95.1 degrees. And then using angle B, I could solve for side B by doing my sine of 35 over 6, sine of angle B over side B. And to solve for side B, sine of 95.1 times 6 divided by sine of 35. Sine of 95.1 times 6 divided by sine of 35, which would make side B about 10.42. In the second situation, if angle C was 130.1 degrees, then angle B would be 180 minus 35 minus 30.1 minus 35 minus 130.1. So in this case, angle B would be 14.9 degrees. We do have a second triangle. We're still going to need to solve for side B by setting up our law of sines ratios. Sine of 35 over 6 equals the sine of angle B, 14.9 degrees, over side B. And once again, to solve for side B, we'll do sine of 14.9 times 6 over sine of 35. Sine of 14.9 times 6 divided by sine of 35 means that side B in this case is 2.7. Approximately. These are rounded, of course. Okay, when you're solving for two separate triangles, be very careful that you are distinguishing the different parts that you found for each triangle. So for example, in situation 1, I have found that angle C was 49.9 degrees. That made angle B 95.1 degrees, and that made side B 10.42. In my second situation, we found angle C was 130.1 degrees. That made angle B 14.9 degrees, and that made side B 2.7. So check that you have two separate triangles when this situation arises. Good luck, and please again text, email me with any questions that you might have as you attempt some